Hello and welcome to another wonderful episode, the first in the season, Fall 2024. And today we have Jake Araujo-Simon talking about categorifying the Volterra series. Okay, take it away.
Sure. So, did you want me to do the introduction?
Yeah, you do the introduction.
Sure. So, about me, I grew up in New York, went to Stuyvesant High School. I did my bachelor's at the University of Chicago in an interdisciplinary mix of music and then some math, physics, and computer science kind of shared equal weights. And then I did more recently a master's at McGill in music technology. And for my thesis work there, I focused on the Volterra series. So this presentation will be about kind of related to that work. And actually, currently, I'm a master's student again. This time in electrical and computer engineering at Cornell Tech here in New York.
Do you play any instrument besides the computer? What do you play?
I play the piano best, and guitar and some others less well.
Nice, very nice. Yeah. Okay.
Okay, great. So, also thank you guys for having me, Nosan and the seminar. So, I'll be talking today about an approach to nonlinear signal processing that aims to be compositional in nature, hopefully shed some light on that nebulous term, still nebulous to me, but somewhat. But that is based on this model from nonlinear signal processing known as the Volterra series. So just kind of to set the stage a bit, why these three things? Why nonlinear systems, why Volterra series, and why compositionality? Well, for the first, all systems in the real world are nonlinear on some level. They might be approximately linear in certain regimes, but can be driven out of those regimes. Also, we might like nonlinear effects, and so by better understanding them, we can either suppress or enhance them. Why Volterra series? There are other models of nonlinear systems or nonlinear behavior. Machine learning models are, of course, much more prominent today, although Volterra series have been used for decades, since the 50s at least, in a wide range of fields. But Volterra series have some nice features, aspects about them. From a signal processing perspective, they extend the most common model in signal processing, which we'll talk about, which is that of a linear time-invariant system, somehow to the nonlinear regime. They, I think, have very nice properties and maybe more interpretable than other models. And then why compositionality? Lastly, well, compositionality is this kind of term in like the applied category theory scene where which is understood in contradistinction to modularity or mere modularity. And just generally speaking, we would like to understand not only how to interconnect systems, but how the properties of those systems change as we interconnect them, and whether there are so-called emergent effects or what have you. Okay, so just as a kind of overview of the talk, I'm not going to assume much signal processing knowledge. So I'll give some background on linear and nonlinear systems, I'll introduce the Volterra series. Then in section 2, I will begin to detail an approach to categorifying the Volterra series, at the end of which I'll define a category, which I'll call Volt, the category of Volterra series. And in section 3, I'll look at some monoidal structures on it. And then if I have time in section 4, I'll maybe outline some connections to this field called time-frequency analysis, and which is kind of at the heart of signal processing. And then I'll just kind of end with some conclusions and also outlook on like generalizations, extensions. And as a disclaimer, one important thing that I will not cover at all is nonlinear system identification. So in practice, Volterra series are used for analysis and for identification. That is to say, we have some unknown nonlinear system. We're either able to probe it, or we already have data concerning its behavior, input-output pairs, and we would like to learn a Volterra series model. There is some work on the relationship between Volterra series and neural networks, and I'm basically not going to talk about any of this today, but it's interesting stuff. Okay, so not going to go through all of this, just setting some notation. capital F for the Fourier transform. T will almost always stand for something relating to a tensor product of some space.
S of R?
What is S?
Okay, S of R is, you can think of, so I'm going to say on the next slide how you can think of it for the first section, and I'll...
Right, but if you're defining notation, capital S should be defined.
You're right. So S of R is this short space, S prime, space of Schwartz functions which are rapidly decaying. The S prime of R, which I will also, so here is actually S prime of R is the space of tempered distributions.
But I'm going to think of it like L2.
Yeah,
Okay.
so L2 includes into S prime of R.
Okay.
So it's functions from the real line to the real line such that
Signals, you're asking?
what's
doesn't exist for L2.
S prime?
Oh, I'm going to give a definition later, a formal
Okay,
definition.
fine.
Yeah. But for now, I basically want to just think of these at a very high level. So a signal, for all intents and purposes of the first section, is just a complex valued function of the real line. The space of signals is the space of all signals, right? Is denoted S of R, S prime of R, and I will define these more precisely later. A map between two signals is written as so. And lastly, we're just going to think of a system for this first section just as some kind of operator on the space of signals.
Wait, what's the map?
What is the map V?
What is a map, L, between two signals?
It's going to be either a multiplier or a convoluter, which I will define later.
Okay.
Yeah. Okay. So a system, linear systems are those which, so I want to define nonlinear systems. Let me start with linear ones. A system is linear if it satisfies superposition and scaling, which are written as so, right? So if you...
I'm sorry, could you just go back one slide?
Sure.
A system can be thought of as V. Okay, thank you.
Okay. So if we add, so systems process signals, right? If we add two signals and then process, it's the same as processing individually. If then it is the same as processing individually and summing, we have superposition, and likewise with scaling, we have and if both, we have linearity, okay? Another important property is that of time invariance, which just means that it commutes with translations. A translation is implemented as a convolution, we'll get to that later, with the shifted delta function. Time invariance is sometimes called shift equivariance as well.
So, you did that too fast.
Sorry.
So the tau is a little bit.
Yeah, the tau could be infinitesimal. The tau is just a parameter of the how much you're translating by.
Okay.
So the delta sub tau is the delta function centered at tau, which is just a real number.
Okay. So what you're saying, the bottom line says, if you shift and then you do this V, which takes you from signal to signal, it's the same thing.
Yeah.
Right.
Yeah.
Okay, now I see.
Okay, so the Fourier transform is kind of a central player. It's the bridge between the time and frequency domains, and here I've shown both the 1D and the n-dimensional cases. The latter is very similar to the former, except instead of a single scalar frequency variable, you have an entire vector of frequencies, which you're dot producting with some vector of time variables as well. And I've shown some so-called Fourier pairs here in 1 and 2 dimensions. So we have that the Fourier transform of a rectangular function is a sinc function, and I'm showing those in both 1 and 2 dimensions. The two most important, the two types of linear maps between signals that we're concerned with are convolution and modulation. And these are dual somehow by the Fourier transform. So I've given the expressions for convolution on the top and modulation below, and the convolution theorem says that these are dual. So taking the Fourier transform of the convolution of two signals is equal to the pointwise products of their spectra. We call the Fourier transform of a signal its spectrum.
So U and V are signals, so you called them S before, but now you're U and V.
Yeah.
And what's U hat? Those are the Fourier transforms?
Yeah, they're spectra.
So you're just using hat to denote F.
Yeah, well...
the two notations are same.
The
it's
image.
like write F of U or put a hat on U.
Yeah, the image under F.
Okay. And the circle with the dot inside?
Oh, so yeah, this is pointwise multiplication. And I'm using it instead of just a dot because when we deal with n-dimensional signals, it's useful to distinguish and disambiguate.
I have a quick question. On the bottom, I guess that
Yeah.
commutation graph, right? You have star V and then you have dot.
Yeah, sorry. So that I guess
Should that be dot V? Dot V
frequency.
hat, basically?
Yeah.
Okay.
Yeah, dot. You're right. Dot. That should be dot v hat.
Okay.
Yeah. Thank
That's
you.
fine.
Thanks. Okay. Oh, and by the way, I'll use modulation essentially as a synonym for pointwise multiplication in this talk.
Why is the arrow going down?
The convolved by v.
Dot V. Okay, fine. Okay. Dot V hat. V on right. Okay, fine.
Yeah, thank you for that. Okay, so putting linearity and time invariance together, we get the notion of linear time invariant system. And the reason, or LTI system, the reason that this class of systems is so useful and important in signal processing is that it's exactly the class that can be represented by these convolution integrals. And so just some notation, what does a linear time invariant system do? It convolves the input signal by a fixed function, which is called the impulse response, or a fixed kernel function called the impulse response. And we refer to the Fourier, so that would be v, lowercase v. And we refer to the Fourier transform of the impulse response as the frequency response of the system. And the key thing here is that, LTI systems simply scale each of the frequencies present in their input by some complex number. So they're potentially gaining them and importing a phase shift. And so they're equivalently represented in the frequency domain by so-called Fourier multipliers, and which are basically diagonal matrices consisting of coefficients that you're weighting the different frequencies by. And so a consequence of that is that such systems cannot add new frequencies. So there can be no frequency present in the output that was not already present in the input under the action of a LTI system.
So this V, the little v, is also in the Schwartz space. Is that right?
It could be a distribution, I guess. But no, yeah, sure. That's yeah.
Do you want to put restrictions on it? Do you want to make it like really
later?
nice?
Can you hold these questions about the? I mean.
No.
Right now.
No, I can't.
Fair. Right now, no. Yeah, you can think of it as a. Oh, so actually, it's a great question. Later, I will define more formally the classes of maps that we're going to consider between signals. There's a class. We will define a class of so-called convolutors, and these are precisely the functions. Sorry, these are precisely the maps that take Schwartz functions to Schwartz functions under convolution. Basically against a tempered distribution. So it's actually a restricted class of tempered distributions that we can convolve by, which will take Schwartz functions to Schwartz functions.
And is this thing where you're multiplying and then integrating convolution? I don't really know.
Mm-hmm. Yes.
So this is just convolution. So I shift S and then I convolute with V.
Mm-hmm. Yeah.
Okay.
Yeah. You take yeah. Mm-hmm.
Okay. Thanks.
Cool. So a system is nonlinear if it is not if it's not linear, but if it's not necessarily linear, right? So we want to include all linear systems in our class of nonlinear systems as well. And we can think of somehow like the nonlinear effects that such a system produces as measuring its deviation from being linear. But nonlinearity as a notion is kind of negativistic, and we would like to understand how these nonlinear effects arise positivistically. And the Volterra series is a model that kind of gives us a way of understanding nonlinear effects positively. So what is the Volterra series? It's a universal model of nonlinear behavior that extends this convolution integral representation of linear time invariant systems somehow to the nonlinear regime. And I'm going to define shortly more so in a number of slides how it does this. But we can think of it kind of roughly. I've depicted Volterra series up to third order here. And one thing to note is that at each order, so 1, 2, 3, each order j, the wire carrying the input signal is splitting into j copies. And so and as a point of clarity, this model is in fact only universal for systems that have what is called fading memory, which means that the influence of events in the distant past on the output of the system in the present falls off asymptotically.
And so the signal is the thing on the left, and then you're like taking S and then feeding it into a bunch of things?
Yeah, you're making copies of it and you're feeding it into these boxes represent what I'll call homogeneous Volterra operators.
Okay.
So let me...
So it's gonna be in a sense linear. It's gonna be a linear combination of the input and then the sort of increasingly higher Volterra operators of the input.
Yeah, exactly. So it's going to be, as you said, it's exactly a sum of the homogeneous outputs in response to the input signal.
Yeah, but the V1 doesn't necessarily could alter it. You understand?
Oh yeah, that's you're right. Thank you. That's as well. So V1, in fact, is exactly a linear time-invariant system. V1 is linear. But it could filter it.
Could you spend a second on etymology? Who's Volterra was?
Oh yes, of course. Well, so I'm remiss for not mentioning him already. I lamentably haven't read his original work, but he was an Italian mathematician from like the late 1800s to kind of 1930 maybe. I should get that right. And he. Yeah, so but his work on these series was kind of not taken up for a while, and then was discovered by Norbert Wiener, who worked on it during the war at MIT with a bunch of people, and at some point made its way into the public domain a while later.
So Volt's battery is from him?
I don't know.
No.
I don't think so.
No, that's 100 years earlier.
Yeah.
Okay, fine.
Yeah.
Volterra.
Okay.
Okay.
So I'm going to kind of maybe not flash, but show you some representations of how we compute the Volterra series. I'm going to show you into the time domain and the frequency domain, and also show it a more compact representation in a couple of slides. So you don't necessarily have to worry about understanding I wouldn't worry about understanding all the math on this slide. The type of, as I said, of
Well, you're showing what the picture really means.
Yeah. So this is the representation of this is how you compute the Volterra series in the time domain. And we see, so there are, a few things to note. One is it's taking signals to signals. Another thing is that the output, which is written here as y of t, is given as a sum, as was pointed out, of the outputs of the so-called homogeneous Volterra operators, which are written these capital V sub j's. And if you look maybe now at the bottom line, so what are the V sub j's? They're given actually as multidimensional convolutions. Between what? Well, between each homogeneous operator is defined by its kernel function. Here is lowercase v sub j. So like the linear time invariant system, there's this fixed function that you're convolving by, but what you're convolving it by now is different. And what it is, it's given here by this product on the right-hand side. So you generate, I think of it as you generate j copies of S, and then you basically you multiply them sampled at different delays. So that the tau sub r's here are in general different delays, and you're multiplying j in general different samples of the input signal together. And indeed, this is some form of tensor. We'll see in a moment, but this is basically a tensor power of the input signal.
Well, one thing, your Vj, so it's a function of one variable?
Lowercase v sub j is a j-dimensional function.
Okay, so it's a function of all the taus you have.
Yes. Yeah, exactly. So tau sub j, so the tau sub r's here are scalars, and tau sub j is basically the vector of tau
the
sub
index
r's.
goes up to, I see the product goes up to j. Okay, so.
Okay?
Wait, so V is the Volterra series.
Yes.
V, that means it's a system.
Yeah.
And then Y of t is the image of V.
Is the image of S under V.
Is the image of S under V. And then Y of j.
Is the output of the jth one of these guys.
Gotcha. Okay.
Well, what was his intention? I mean, every signal could be written as a sum of sines and cosines.
I think, if I'm not mistaken, he was looking at a problem in like fish ecology or biology.
No, but
Sorry.
I think this was something different because.
Please.
So why would I understand Volterra's series was, he was studying integral equations. There's some kind of equation known as a Volterra integral equation. And the way you solve it is by iterating and get a series of this form. So I believe Volterra's thing, because that's well known, you could read Percomi's book or anywhere, he studied, an integral equation named after him, a standard way of iterating. And so my guess is, I'm not a historian, we should check, was that, and that was certainly well known. Now, Wiener may have been the one who said, oh, I can apply this also to doing signal processing, not just to solving integral equations.
Thank you, Ray, for the, yeah, that's...
But I'm not sure, one should check, that's my best guess.
I should have checked. But it's interesting to hear, yeah. I'd like to know the history better.
Yeah.
Okay. So I want to show some other representations of the Volterra series, because this is not the easiest one to work with in practice, the time domain one. So in particular, we have this, well, the frequency domain one is preferable it's a bit simpler to interpret in my view. So, so in the frequency domain, I have two expressions here. One for the time domain output, and then on the second line, we have a direct expression for the spectrum of the output. So there's some kind of inverse, on the top line there's some kind of inverse Fourier transform going on, but you also have this summation going on in the argument to the exponential. And the second line is the kind of really curious one, because if you look at the domain of integration, there's a restriction on it. And basically what we're doing here is we're actually, on the right hand, now instead of a convolution, we're taking a product of what? Of the, what is called the Volterra frequency response function, which is the Fourier transform of the kind of higher order impulse response function of the Volterra operator at order j. And we're now, instead of a convolution, by the convolution theorem, which extends, of course, to any dimension, we're now taking a pointwise product of that. And what? Well, this is just exactly the tensor power of the input spectrum, S hat. Sorry. So I'll write that on I'll show that on the next slide. But before I do, let me just remark that this domain of integration, this restriction on it, what we're doing here is we're integrating really over hyperplanes that are perpendicular to the diagonal. So I didn't highlight this, but in the time domain, somehow what we're doing in order to obtain a one-dimensional output from the j-dimensional convolution is that we're slicing along the diagonal. We're indexing this j-dimensional thing along the values of the form t, etc. And you could do otherwise, by the way, but this is how it's canonically defined. And then here what we're doing is in order to get the value of the spectrum of the output at some scalar frequency variable omega, we're integrating along hyperplanes, all of whose points have coordinates that sum to omega. And this follows from a theorem known as the projection slice theorem in Fourier analysis, and there's some connection here also to the radon transform that I don't really understand.
One thing, just a purely technical point, I say capital omega and a little omega, so it looks like the little omega is a variable integration, but then capital omega domain, but then it appears as an exponent, so I'm just having trouble parsing this.
Yeah, thank you. I didn't write it here, but capital omega is just the vector consisting of these little omega subcubes.
Oh, so this is again, the j is the number of inputs, got it.
Exactly, yeah.
Got it.
Okay.
So thank you.
Sure. So at a high level, what's happening here is that, well, okay. You could think of the Volterra series basically as representing nonlinear effects via really what are harmonics that are generated via intermodulation between frequency components in the input signal. And then it's also filtering these frequency components. Yeah, and I've just added a reminder here that the first order Volterra series is simply a linear time-invariant system.
I'm sorry, so
yeah.
For the Volterra series, what is the input for the system? The input are these little VJs, right? The little things you're convoluting by.
No, sorry, the input is a signal S. So
No, I know that. I mean like the parameters of
yeah, sure, yeah, exactly. The parameter Volterra series is defined by its kernel functions at each order. The kernel functions at each order j.
Okay, and then so I'm thinking of it like, I take a system, I do this complicated thing with these other signals,
Yeah.
Like how is there a way to think about it, or?
Yeah, so maybe this slide will help. So,
one second before you go.
Yeah.
Back up to the colorful slide. So if S
Yeah.
is linear, then you would only need V0 and V1. Is that the point?
sorry, if the system or the
Right.
yeah, then yeah, exactly. So if it's a linear system, you would just have V1.
Just V1.
Yeah.
And the rest would be somehow outputting 0 or something.
Exactly. You could just have kernel functions equal to 0 everywhere.
Right.
And V0 is a constant. I don't know if I said that.
And one second. So V1, V2, V3, they're and Vn,
Yeah.
they're measuring how far you are from being linear, and
Yeah. I mean, I don't know if it's the
you have a hierarchy of functions.
yeah. I don't know if it's the best way to think about it is in terms of deviation from linearity. The way I think about it is that at order j, you're generating. Okay, so actually, if we look here at the product, what we're doing is we're taking products of j frequencies sampled from the input, and when you multiply these frequencies together, when you multiply these waves together, you add their frequencies. So we're basically generating all possible frequencies that can be obtained as sums of j frequencies from the input, and then you're filtering, and then the Volterra series is furthermore filtering all of those harmonics, all of those, their intermodulation components, as they're called, by each one of them by a complex number. Each one of them corresponds to a point in multi-frequency space, and then there's a weight, there's a complex number weighting that particular multi-frequency.
Can I say something that might be silly? This is what I'm sort of envisioning in a way, which I think corresponds to like you've got two lines going in or whatever, is, right, if I've got a linear transform on a function, then if I know its value at a point, I can then determine its transform value at that point. And one way I think about what's happening here, and I could be totally wrong, but it seems to me like, so I can't just know the value at that point if I've got sort of something that's like V2. I have to know it at 2 points, right? Because I've sort of got, I'm looking at my original thing and I'm looking at some rescaled version of it that sort of got like half the speed or double the speed, and then I can be a function of both those points. So I'm moving along sort of the time dimension at 2 speeds. And then if I'm at V3, I'm going to be like, it's going to be like, a rabbit, a tortoise, and, a slug, and they're each moving along the time dimension at 3 speeds, and then I can linearly combine their 3 different observations. And I think that might sort of capture what's happening.
I think that sounds great, yeah. I've been trying to think of a physical semantics for this. It definitely involves delays and, yeah.
Yeah, so these are delay differential equations.
So
delay integral.
Yeah.
So an n polynomial is defined by n points,
Yeah.
n plus 1 points, and
Yeah, there is a connection to polynomial stuff here. Yeah. Okay, I think maybe this is kind of just expressing notationally what I've been at least alluding to here, which is that what's going on somehow is that we're forming these tensor powers in both the time and the frequency domain, and then in the time domain we're convolving against the kernel function, and in the frequency domain we're just pointwise multiplying. And so, in the frequency domain we're additionally projecting or integrating, whereas in the time domain we're slicing along the diagonal. So somehow there's the interaction of these various operations gives you all the kind of math of the Volterra series. And so this diagram on the bottom is kind of depicting that. If we start with in the lower left with a signal, we first kind of pass to the Cartesian power, we generate j copies of it. We then obtain from that the tensor power of those copies of the input signal. We convolve by the kernel function, and then we slice or index along the diagonal to obtain the one-dimensional output of the series. This is just at order j. So
and h bar is the composition of tensor j and dot vj, right? Correct?
Yeah, good question. I think I'm trying to express some kind of property here about equivalent linear maps or something like that. But good question. I haven't defined it. Okay. So that's kind of like I want to get to the categorical stuff, but that's kind of just the mechanics of the Volterra series. I've told you that Volterra series can represent systems. Here are 3 systems. The first 2 are linear. And I'm just giving you the kernel functions of the Volterra series representation of that system. So the first 2 are well known in linear signal processing. If you time shift, it's equivalent in the frequency domain to delay, imparting this phase shift. And if you differentiate, you have this that's going on. And the most interesting maybe is the simplest nonlinear system is what you might call the memoryless polynomial. And what that looks like in a Volterra series is just at order j, the frequency response function is just constant. So you're generating all possible harmonics and you're weighting them all by the same complex number. Okay, so I have a little audio demo here. I don't know if everybody's going to be able to hear it, in particular the first thing. It's not that important. It's just a sum of 3 sine waves. They happen to be low for reasons. The output of that, and then I'll play the output of that under a 3rd order Volterra series. No filtering happening, just harmonics generation. And then I'll play you some actual audio samples.
Make sure your volume is as loud as possible.
Oh yeah, thank you. Yeah, looks like this.
Good.
All right, so I don't know if it's very low, okay? Just 3 sine. I'm going to show a plot of the first 2 on the next slide, so don't worry if you don't hear them. And then the output of that under the 3rd order Volterra series. So it bumps it up basically by a multiple of 3. And it actually is also generating additional harmonics, which I'll show in a moment. Here's now a cello little thing. Okay, and its output under the Volterra series is going to be distorted. So it doesn't sound very nice. There's no filtering going on. It's just generating all possible harmonics at order that can be obtained as a sum of 3 frequencies from the input spectrum. And so here's a plot of what's happening in the first pair of examples. We have the input signal, which is the input and output signals on the top row. There's spectra on the middle. So you can see the input is just a sum of 3 sine waves, and on in the output we get this cluster of frequencies. And if you're thinking it looks like a Gaussian, a kind of discrete approximation to a Gaussian distribution, well, it is. It's actually a 2D projection in this case of a 3-dimensional Gaussian. And if you count the number of peaks, they're exactly 10, which is the number of, happens to be the number of weak 3 compositions of the number 3. And if you look at the amplitudes of these different peaks, if you normalize so that the lowest is 1, these are given by actually the certain multinomial coefficients. So there's some multinomial combinatorics that is showing up in the math. Okay, so now what I want to do is I want to try to, the idea is that the Volterra series should be a functor. We would like it to be a functor. In order to try to define it as a functor, I have to tell you what the kind of base category its domain is. So let me try to, that's what I'll do in this section. Okay, the high-level idea, kind of as before, is that the objects are going to be signals. The morphisms are going to be what are called convoluters or multipliers between signals. And the reason why we're going to work in this space S prime of R is because the Fourier transform, it is precisely for this space that the Fourier transform is well-defined. So, okay, so unfortunately I'm using a different script here, but this is the same space as S of R and S prime of R. So the Schwartz space is this space of basically rapidly decreasing functions, sometimes referred to as test functions, technically which decay faster at infinity than any polynomial. And they kind of, bump functions, they're sometimes called as well. Well, those might be examples of Schwartz functions. The tempered distributions are, the space of tempered distributions is the space of linear, so continuous linear functionals on the Schwartz space. So it's dual to them. I'm not going to really use this pairing notation actually, but they're not functions. They're things that take Schwartz functions and return some value. But we can basically think of them as functions. So in particular, here are two distributions that are in the space of tempered distributions, but not in the short space. The delta distribution, you can think of as like an impulse centered at 0. It should have like infinite, technically, amplitude at 0 here and like 0 width, but or infinitesimal width. But and the maybe less familiar is the Dirac comb, which is given as like the periodic extension of the delta function, and which we'll see more about in a second. So now I've told you the objects or the elements of these spaces and I wanted to find now morphisms between them. So there are two classes of maps that we will care about, and they happen to be dual once again. So the first is the space of multipliers, and the main idea is that multipliers are those maps which take Schwartz functions to Schwartz functions under multiplication. And similarly, convolutors, well, so I'm not going to worry about this technical definition. The idea is that they are precisely the maps which take Schwartz functions to Schwartz functions under convolution. And the Fourier transform is a linear bijection between multipliers and convolutors, or the space of multipliers and the space of convolutors. So now I can define, I can find two category-like things. The first one is not actually a category, only a semi-category. So S of R is
what is the semi-category missing?
Potentially identity morphisms at its objects. And so S of R is the semi-category with object Schwartz functions and morphisms multipliers between them. Why is it not a category? Because the delta function is not in the space. And we need convolution by the delta function centered at 0 to have an identity morphism, or equivalently, pointwise multiplication against the function that is constantly 1. But the space of tempered distributions has these objects.
Well, we said without, what are the objects in this category, or do you get to pick any set as your objects, or
in
S
prime of R? In S of R, S prime of R.
Either one. It says with object, but what are the objects? Is there a specific set of objects?
Oh, they are tempered distributions.
Oh, each distribution is an object.
Exactly.
Oh, got it.
Yeah.
Okay.
And by the way, the Schwartz functions are included into this.
So the first comma should actually be as, with objects as Schwartz functions.
Oh, well,
and morphisms as multipliers between them.
I guess that would be clear.
Yeah.
Okay.
Can you give an example of two objects and a morphism between them in the second category?
The second category, sure. So pick any signal, that is, pick any Schwartz function. Convolution against a delta function, so identity morphism is an example of that would be a convolutor.
That's the identity function?
Yeah, so if you convolve with a delta function that is centered at 0.
Doesn't that pick out at 0?
Now if you convolute with it.
Oh, you're saying if you apply it to it, then it picks it out at 0.
Well, you've got these two, you convolve with it, right? And
okay.
Then, right, that's sort of...
Okay, so I have an arrow from S to S prime.
Yeah.
S prime can be written as take S and then convolve it with something else.
Exactly.
Okay,
yeah.
okay, I got it.
Okay, one second. I have stupider questions. I have a really stupid question. What's tempered?
Yeah, I think it, great point. I didn't say this. Convolutors, so whereas Schwartz functions are rapidly decaying at infinity, convolutors are slowly growing. So they have polynomially bounded growth, I believe.
So in this category, right, it seems like you set it up sort of like a monoidal category, right, in that every morphism is going to come from a pair of objects, right? So like if I have an object A, then all the morphisms from A are going to be represented by an object B and the action of multiplying with it or the like, right? So, which is not any old category, right? This is a category where all your morphisms are generated as binary operators between two objects.
Yeah, I'd like to understand that better. I've had like thoughts in that direction.
Yeah.
I don't interrogate the structure of the base category at all, and I think it has interesting structure that I'd like to understand better.
Oh, you go too fast.
Sorry?
So the Dirac delta is a tempered distribution, but it's not a Schwartz function?
That's right.
It's not any kind of function.
Say again?
It's not any kind of function. It's just a
It's
distribution.
not a function. Oh, right. But, good lord.
Okay.
What's a filtered structure?
Oh yeah, I didn't say that. So that point that I made earlier about how linear time-invariant systems can't produce new frequencies, you can think of convolutions are given by Fourier multipliers in the frequency domain. They can send frequencies to 0 amplitude, or they can just kind of keep them around. They can't add new ones. So you have, maybe I'm speaking kind of vaguely here, but I think of this as having a filter structure in that you can only go under convolutions to signals that have less rich spectra.
Oh, I see. Okay, so you have like, for every object, you can think of it as like a sum of frequencies.
Yeah.
And then you're saying like a map can't add new frequencies. It can only like destroy it.
A linear map, a convolutor, exactly.
Right. So this map, so this particular category called base category only has the linear structure in it so far.
Yeah.
The nonlinear thing is yet to be added.
Yeah.
One other really simple question. So would another object would another tempered distribution be Heaviside step? Is the integral of the direct delta?
I think that's a bona fide function, or that, right? It might not be. It might not be. It might not be a Schwartz function actually.
Well, it's not.
Oh, it's not Schwartz.
Not Schwartz, but it's tempered. But it is.
Yeah.
But it's obviously linear, bounded by a constant.
It's a distribution, but it's not tempered, right?
No, tempered. I thought you said tempered was.
Oh,
yeah.
Because it's not going to drop. It's got to drop off to 0 at both sides.
If it's Schwartz, if it's tempered, it just has to not grow quickly.
Oh, okay.
Which this does, because
Yeah.
it's bounded by a constant. In
Yeah.
fact.
Yeah. Okay. All right. So as Ray just pointed out, I haven't. This is just the base category on which we want to define the nonlinear stuff. So we want to define the Volterra series as a functor on this base category. So to motivate that, we could note. Okay, so the Volterra series maps input signals to output signals. What happens if we morph the input? So we can look at that kind of. We can depict that as so. We have some signal. We have some convolutor L from S to S prime, and then we get this pair of nonlinear outputs V of S and V of S prime, and we can ask, well, is there a map V of L? Not such that this diagram commutes. Just is there such a map V of L? And the idea for how I want to define V of L is that I just apply. The idea is to apply L simply to each copy of S occurring in the Volterra integral at order J.
How am I supposed to think of S now if it's not a signal? You have now the distribution is like...
You can think of it as so the cool thing about, or the important thing about convolutors is that they take Schwartz functions to Schwartz functions under convolution somehow against like a tempered distribution, a certain restricted class actually. So the objects here are still signals actually. You can think of signals as tempered distributions as well. There's some. I'm not an expert in functional analysis, but people look at like the Schwartz representation theorem and stuff like this, right? Somebody should correct me if I am misspeaking. But you can think of the objects as signals, and then but we want to be able to convolve them by distributions, or if does that kind of make sense?
Now V of L should be on V of S. Is that right?
Yes. Thank you for pointing that out. I'm making I chose to be lazy and try to use an abusive notation here, and it does make it more complicated, or more confusing. And you're absolutely right. V of L is a map from V of S to V of S prime.
So it should be V of L of V of S at...
Yes.
Okay.
Thank you. Apologize for that notation. So if we apply L to each copy of S, we can look at that equivalently in the frequency domain. So here I'm by the way, I'm making the same mistake that you just pointed out. This should be V of M applied to V of S hat. Basically what I'm trying to say is that we have we're looking at this map V of L now in the frequency domain as a multiplier instead of a convolutor. And I'm also furthermore distinguishing between the multiplier itself, M, and the weight function, the thing that the function by which it weights the different frequencies in the spectrum. So, but the key thing is just, or the thing to maybe note here is on the last line. If you just push basically this multiplier through, you end up getting you see that it ends up being just an additional filtering on the tensor. So we're now filtering by the tensor power of the multiplier function. That's sorry, by the weight function of the multiplier. We're doing an additional filtering.
Does filtering just destroy like frequencies or something?
It may, but it can also shift their phases and impart a gain or a change in magnitude. So we can now verify that whether the Volterra series is functorial by asking what is its action on a composition of two convolutors. And because in the frequency domain you're simply multiplying their coefficients at each frequency, the coefficients by which they weight each frequency, this is basically just asking whether whether filtering by the tensor power of basically the product of these weight functions is equal to filtering by their tensor powers individually. And indeed, that is true. And similarly for the spectrum of the delta function is just constantly 1, so it does nothing, so we have identities. There is a caveat, I think, which is that if you have perfect destructive interference, then it may not be the case that the spectrum of V of S prime is less rich than that of V of S. Somehow, if you have, and in which case the denominator here would be 0, but when the numerator.
So for example, if I have a frequency doubler, I lost my original frequency, I got twice the frequency.
I think would that be? Oh yeah, due to cancel. Yeah, I think that could be bad.
Yeah, for example, I had a simple thing, gave twice the frequency, but I lost the original one in the process.
Right. Yeah. Yeah, there are examples you can construct where like the you have but anyway, I didn't want to dwell on it, just a possible caveat.
No, so, I'm just mentioning the simplest counter examples.
Yeah.
That's all.
Thank you. So now let me give I'm not gonna dwell on any of these. I'll give an example, I'll just maybe point out the output or the results. So when it comes to translation, what happens if we kind of morph the input to a Volterra series? If we translate the input to a Volterra series, it turns out it commutes. The Volterra series commute with translations, which you should expect because they're a kind of convolution type.
So right now you're trying to prove that V is a functor.
I claim to have maybe somewhat vaguely already shown it.
Oh, okay.
Yeah.
So then why are you...
I'm just giving you some examples now, and a couple of slides of examples of for a particular type of morphism in the base category, what is the action, what is its image under the action of a Volterra series? So translation is not very exciting. We can also modulate. If you modulate the input by a pure frequency, that's equivalent to shifting, to imparting a frequency shift to the spectrum, right? Because multiplication in the time domain is convolution in the frequency domain, so we're convolving by some shifted delta function, which shifts the entire spectrum. So you get something like the same filtering thing, just with now a shifted version of the tensor power of the spectrum. And this case was known in the literature, or at least I found an example, and it reduces to that if the input signal is constantly 1. Periodization is this operation of you take a signal, really what you do is you convolve it by a Dirac comb. And if the bandwidths line up, it produces a pretty picture like that. But yeah, I mean, just to note one thing, at the bottom line, we're getting these multinomial coefficients. Maybe you can leverage some sparsity or something and try and compute things. And similarly, for sampling, we also get some cancellations occurring, so maybe some sparsity. Okay, so that was kind of functorial stuff relating to the Volterra series, but I want to try to get to one more level of categorification. So, or in this process of categorification. So, I've told you that Volterra series model systems, but systems change too in the real world, right? So we'd like to have some kind of notion of morphism of Volterra series, morphism between Volterra series, and being as they're functors, we'd like such morphism to be a natural transformation. So as this notational aside is not too important. So far, I've just treated this index of the operators as an integer, which is kind of assuming that there's one homogeneous operator at each order, each kind of level or dimension. But you might, for example, if you sum a series, now you have like two operators of the same dimension. So you'd like to index all of these homogeneous operators. So I'm just using this bracket notation to distinguish an index from the order of nonlinearity of the operator that it is indexing. And then I'd like just a symbol to denote the set of all homogeneous operators. So little lowercase I is an element now of I sub v. And it turns out you can actually query or somehow compute this set of homogeneous operators by feeding in the constantly 1 signal, because it, or at least under the assumption that the 0th frequency component of the Volterra kernel functions is 1, sorry. But don't worry about that right now. Okay, so I'm going to give a definition now of a morphism of Volterra series. And it has a few pieces, and if you're familiar with the concept of a lens, this is an example of a lens, or it has a lens structure. So given to Volterra series V and W, a morphism phi between them is going to kind of be comprised of the following pieces. First, you give a function between the index sets. So for each homogeneous operator in the source series, V, choose an homogeneous operator in the target series. And then for each such pair, so for each such, we want to, the idea is that, or like, where we're going is we want to be able to compare somehow the kernel functions from the different operators. And we're going to try to use a pullback to do that. So then, after you've chosen such a pair, give a map from between the domains of the function spaces, so from Ri to R phi sub 1 of I. And then this, and then additionally, we're going to need a weight function over the domain of the source series, which is here is C. And then from this data, you can obtain a map which I'm calling the weighted pullback. So you pull, and I'm going to show actually how that works on the next slide. Here I'm defining it just for arbitrary elements of these spaces, but I'll show it on the next slide. Well, here in terms of the kernel functions, which is the thing that we're trying to pull back.
Sorry,
yeah.
Is I of v the set of the little functions vj?
I'm thinking of it as the set of the operators, which are parameterized by those little functions.
So the big vj's.
Yeah, yeah.
But they determine each other, or
yeah,
the big vj is determined by little vj.
Yeah, yeah. So you could think of it as that, actually, sure. Okay, so so from all that data, we can then obtain component morphisms, these phi sub s's, and how does this work? Well, basically, on the the second to bottom line, you pull back the kernel function of the target operator you've chosen, so written W sub j here, and then you weight that by the weighting function, and you're using this as an additional filter now on the product of your source kernel function and the tensor power of the input signal. And I've just expanded that in terms of the pre-composition that the pullback is doing on the bottom line. So somehow we're now pre-composing by this map phi, and then additionally weighting. And maybe that is one reason to expect that naturality should work, since the way that we did, I mean, I kind of skirted over it in a bit, but the way that we defined the action of a Volterra series on the morphism was on some level via what you can think of as post-composition, post-composing by the convoluter. So each copy of S we applied the convoluter to. Here we're now pre-composing, but I'm not going to make that too precise. I'm just going to show this, that if you try to follow the paths explicitly, you find that they produce equal expressions. And there's one maybe thing to note here, maybe it's slightly illuminating, is that if we had chosen this weight function, if we had tried to multiply in the time domain instead of in the frequency domain, this wouldn't have worked. This would this square would not commute because modulations and convolutions don't commute. So you need to be able to commute some of these terms in order to have equality. And there is a technical restriction on the map phi, which is that it should preserve weak compositions of frequencies. And the idea, I guess, here is that you want the systems to interact with the same set of composite frequencies. But really, the reason I'm putting it is just because we need the map phi sub s to be well defined as a linear map, as a convoluter. Which is to say, once again, we can't send frequencies that are present in the source to non-zero terms that are not present in the target.
So if it satisfies this, then it is a natural transformation?
Yeah, I mean, that's what I'm claiming. And here are some examples of Volterra series morphisms. I'm just going to highlight two things. One is that if you choose all maps to be the identities, you actually don't get the identity morphism. You get what is called what I'm calling the auto-convolution. And maybe it's misplaced, but just as like a way of thinking about this, I like the idea that the simplest thing that a system can do is not to do nothing. It's actually somehow to like act on itself by its own frequency response. Because the spectrum of the auto-convolution is you're basically squaring the spectrum.
So wait, so a map between Volterra series is simultaneously a lens and a natural transformation?
Yeah.
I don't understand that. So you're saying from the lens I can get a natural transformation?
Yeah, I mean, I guess the lens is a bit more general. I'm just saying this map has the structure of a lens, and then, okay, I understand your question. Here I'm defining, from this lens data, I'm defining these component morphisms.
Okay.
And these component morphisms assemble into a natural transformation.
Yeah, so from the lens you get a natural transformation. I see.
Yeah.
Okay, thanks.
So in order to get the identity, then you actually want to take as the weight function the reciprocal of the spectrum of the kernel function, of the frequency response function of the operator, of the Volterra operators. And lastly, you can do things like, so translation is another example of a morphism that is perhaps more interesting because it's parameterized. So in order to define a translation, you give now not just a single scalar variable tau that you're translating by, but an entire list of tuples of variables that you're translating by, potentially different amounts and along different directions and different dimensions. And so by varying these parameters, you can actually generate an entire indexed family of Volterra series morphisms. And
That's very interesting.
And now we can define a category, which is the category that has Volterra series as its objects and these kind of natural transformations as its morphisms. And these maps H, the composites, are kind of what you would expect. So H1 here is just a function given by function composition. And then it's a function between sets, the index sets, and then H1 pound is you're pulling back by the composition of the maps that you're pulling back along, by the respective maps that you're pulling back along. Okay, I don't have much time left, so I'm just going to kind of very quickly go over just tell you about some ways that you can interconnect or connect Volterra series. So there are three, and I should say these are known in the literature. So people have studied like what are some rules, what are formula by which, given two Volterra series, you can obtain their sum, their product, their series composition. And what I wanted to do was look at their properties, their universal properties. So for the sum, it's not exciting. You just add the kernel functions. You're adding the homogeneous operators level-wise, which is equivalent to just adding their kernel functions. And we can ask if it satisfies the universal property of the coproduct, and it does if we just take the maps to be kind of what they should be, so nothing too crazy. The Cartesian product, the product is, so for the order of nonlinearity doesn't change if you sum two Volterra series, it's just the maximum of whatever the highest one of the factors was. For the Cartesian product, the orders of nonlinearity, the maximum orders add. And it's because there's some kind of binomial structure going on, right? It's like basically polynomial multiplication. And which is, by the way, I haven't spoken to, but there's some analogy here to polynomials.
So it's Cartesian and it's co-Cartesian. And besides that, it has the monoidal structure.
You'd have to, I'm not well versed enough to say
products
yes.
and co-products.
Yeah, okay, yes. Thank you, yeah. And so here's just a diagram of like what the Cartesian product kind of looks, of two Volterra series looks like. So each of the internal boxes are now homogeneous operators of orders 0, 1, 2, 3, left to right. And we can see that we're basically combining homogeneous operators from the two series and their orders have to add, right? And we can ask if it satisfies the universal property of the product. And it's actually similar to, I think, somehow to the sum because, well, yeah, it's once again function composition for the maps between index sets. And then for this guy, I guess you're pulling back along the pair of maps that you pull back along respectively. Now, by far the most complex one, interesting one, is series composition. And I'm not going to go too much in detail into this, partly because it actually implicates multivariate Volterra series. So what happens is, let me just flash the diagram for it. We're now taking outputs from different homogeneous operators in the series A and feeding them as inputs, which are in general different, right? And we're feeding them as inputs to the homogeneous operators in the series B. So the operators in B now are treated as multivariate. So they're taking in general multiple different input signals.
Now, I just want to say something. So,
yeah.
Jimmy, I'll go back to that. So there's something a little bit weird about this in my mind because when I see a string, this kind of looks like a string diagram to me in a monoidal category, but the string diagrams, those would be the morphisms. But here, this is an object.
You mean this whole diagram?
Yeah.
Yeah.
Well, it's an object in Vault.
Yeah, it's an object
we
in
can
Vault.
think of Vault as actually the category of morphisms in sort of the endomorphism category on SR.
Is that true?
Yeah.
Okay, cool.
That works.
So that's where a lot of the structure comes from. Is we can think of Vault as building these sort of funky, crooked polynomials over SR. And then that's monoidal.
Yeah.
That's how you get a monoidal category often.
Would you mind flashing the previous slide that was similar to that?
Yeah, for the product.
Okay. I see, that's interesting, okay.
So here you're still combining them level-wise.
Yeah, yeah. And the other one, you're combining them all.
Right, so this one is non-commutative.
Yeah.
So the order of, in which you compose them matters.
Yeah.
Right, so you've got addition operation, a multiplication operation, a composition operation.
Yeah, yeah. And so one thing we should care about with respect to the series composition is whether it's associative, right? And we have this equation on the bottom here gives an expression for the kernel function of the composite series in terms of the kernel functions of these factors that are getting combined from the kernel functions from these factors, from the factor series, sorry. And so you can actually try to prove associativity by substituting this equation into itself. There are two possible ways that you can do that. And that's kind of, I'm not going to show that here, but that is what I did in the paper. And I hope you'd be convinced if you read it that indeed it produces equivalent results. And so here's just the theorem, which says that series composition is associative for Volterra series. And just to kind of try to give maybe some intuition, well, you have these complex diagrams that you've obtained by basically kind of substituting the former one into itself. And you can do that in one of two ways. Here's one way, one depiction of one of the ways. Here's a depiction of the other ways. If you count up I've hidden some boxes here. If you count up all the boxes of each of the different types, you get the same number.
And that very much is going to be a string diagram type proof, actually.
Cool. Okay, I am not going to do this section, except to tell you that time frequency is analysis is really cool. It has connections to quantum mechanics, which I don't understand. It has connections to symplectic geometry, which I don't understand.
Well, you can come back in 2 days for the latter.
Oh yeah, that's right, the first, wait, what? Oh,
Well, because on Friday morning, they're having, in the cellular structures, they're having some talk about symplectic geometry.
oh, awesome, great. Yeah, so there's some nice, okay, I won't go into it. But there's an analogs to like Heisenberg uncertainty called the Gabor limit, and the Heisenberg Weil group of translations and modulations and all this stuff. And there are these nice transforms from time frequency analysis. So there's a really nice one called the Wigner-Ville distribution or transform. And it turns out you can represent a very large class of time frequency transforms, bilinear transforms, as Volterra series. So these are then objects not exactly involved, because you need slightly more general notions of Volterra series. In particular, you need multivariate ones, and you also need ones that are parameterized. But then you, for example, the kernel function for the Wigner-Ville distribution as a Volterra series is given as this. So it's a product of a delta function and a complex exponential.
So here the parameter is just this theta.
Exactly, yeah. And okay, that's what I wanted to talk about. So I've said all of these things over the course of the talk. Let me just briefly end by saying about so maybe as a disclaimer, I'm sure some of this could be made more rigorous. But nonetheless, I'm excited about potential extensions and generalizations of those portions of it which are sound. And so one way is Volterra series. So I've treated Volterra series that process signals which are defined over the real line. But there's lots of interesting work happening in signal processing about ways of about doing signal processing for signals defined over more general types of spaces or other types of spaces. Things like graphs. There's a whole field of graph signal processing. Things like topological spaces. There's a really interesting work going on so-called topological signal processing. Michael Robinson has a book about this. Georg Essel has actually done work applying this directly to audio already and to sound synthesis, which is really exciting. But you can look at signals over manifolds, stuff like this. Simplicial complexes, there's simplicial signal processing.
Well, do you mean by that the fact that you are Schwartz function find a real line, now we're saying replace the real line with some other kind of space?
Yeah, exactly. Yeah.
Okay.
And then also, I've explored, I only scratched the surface, I'm sure, of the categorical structure that might be here. And so I'd like to understand that better. One thing I didn't highlight at all is, but which was very important for me, at least starting out, in terms of some analogy to hold in mind, was that there might be a connection to this work that's been going on in applied category theory of polynomial functors. I am not confident enough to make some kind of assertion as to a real analogy, but I think there's a connection. And so it could be interesting to look at connections to poly, especially the work done by New and Spivak, maybe use that as a roadmap of sorts for in covering further structure. And then finally, I think there are all these transforms in signal processing that are really interesting. Things from time frequency analysis, other things like the Riesz transform, which I could name all sorts of things. I would like to understand what roles they play in, if they can be represented by Volterra series or maybe interact with Volterra series in interesting ways, what roles do they play in that category or in relation to it. And then finally, as I mentioned at the beginning, I didn't treat nonlinear system identification at all, but one of the motivations potentially for looking at, for trying to do nonlinear signal processing with Volterra series compositionally is so that you can also go in the other direction, potentially decompose, well, I'm taking poetic license here, but in general, we would very much like to be able to identify nonlinear systems, not by probing them directly, but by probing subsystems, and then somehow assembling information that we get in order into a picture of the entire system. I think that's it. So nonlinearity can be a lot of fun. Thank you all for listening very much, and thanks for the great questions.
So, there's a real life string, what a string diagram looks like in real life.
Modular synthesizers are, I think, a fantastic application domain. Hopefully.
Any questions? That's a great talk. Go.
Can you just go back to them? So for poly, the connection you said was the idea of you have a Volterra series, you have an indexing set, which is a set of these like operators, little VJs. So a polynomial functor has a set of positions, and you're saying these are the positions, and then they also have sets of directions for every position.
Yeah.
So I fix one of the little VJs, and then what do you think of as the directions?
I think of the direction as the dimension. So the number of the direction set, the cardinality of the direction set, I think of as the dimension of the homogeneous operator at that index.
What does that mean?
So I mean, so in the third order operator, we're forming this third tensor power of the input signal, and what that really is doing is, I mean, it's you're indexing into you're forming the space of all possible triplets of samples or frequency components, and so I mean,
Is there like a really like simple example you could think of maybe?
I don't want to. I'm hesitant to not misspeak, but I would love to. Yeah, a nice example would be of the form of like here's a kernel function that maps on almost directly to the discrete case with sets, but I don't. Yeah, I don't want to misspeak.
Okay.
Yeah.
Okay. And then just a comment for myself is that what's interesting about poly is not necessarily the objects, it's the morphisms, right?
Mm-hmm.
The morphisms are the really interesting part of poly. But here it seems to me like the really interesting things are the objects, the Volterra series. Because you didn't really talk very much about morphisms between Volterra series, right?
Yeah.
So it looks to me almost like what you're really interested in is thinking of the Volterra series as morphisms. Just a thought.
Well, from what he did say about the morphisms, they look quite interesting too. He hasn't developed them. So the next question is, okay, I've got a system that does sign to my signal. Let's have an engineer. I want a different system. Well, how do I, design the thing I want? Maybe I apply one of these morphisms to the one I
But
want.
it screamed to me that it's a two category.
I was going to suggest something there actually, which is going to be to make a little pun about, or quip about when Nelson started and said, maybe I want to understand categorification one of these days. Categorification, one slogan of it is you're fattening up your objects, and that's how you move up a level in categories. You turn your objects into morphisms, your morphisms into two morphisms, and so forth. And the move here, though, actually, that you took eventually was sort of, as pointed out, sort of the opposite, which is you took your morphisms in SR and you created a category of them. And so that step, I would suggest that that's what we would tend to call decategorification, right? Which is when you sort of flatten down the level. And then if you didn't flatten it down, but actually preserved it and looked at the full two or n categorical structure, then that would sort of be the actual categorified beast, but then, yeah, you would be in like two category land at a minimum, and might be a bit less pleasant, even if it's more elegant. And then the other thing, I was going to mention just in terms of the polynomial stuff is one way to think of where polynomial functors arise is that in the very nice case, not the general case, they can be characterized as sums of representable functors.
Yeah.
And what you've got in these Volterra series, obviously, is they're summing over, sort of these multiple kernels. And so if you characterize this sort of like these two kernels, these three kernels, or so on, as something, they're not exactly like a representable functor, but they're sort of a, and in fact, that's sort of the whole point, is that they're not representable, which is why you want to, in your SR, right, they're richer. But they're...
Yeah, you might look at S of R to the some power, or the tensor, or like the tensor algebra maybe.
Yeah, they're sort of like, I don't know exactly what I want to call them, and you probably would have a better idea, because you've already, convolution means something else here, but they're sort of like, these doubling functors that are, they're not exactly representable, but they're like representable from some bigger indexing set or something, because and what you really have with Volterra series is there's sums of those instead. And that might be some notion of relating it to poly, would be, instead of doing it directly, is to say, is there like a general Volterrification sort of like thing that you can do if you give me any old base category that's not as specific as something with R's and C's and whatever, and then there's a categorical move where you then generate functors of this sort, and you sum over them, and that gives you the Volterra space on a fairly arbitrary category, maybe monoidal or something. Is all the structure you need to get off the ground.
Yeah, I think you just need to be able to, I'm not sure I follow exactly, but if I do, I think you just need to be able to take tensor products, Fourier transforms, stuff like this. Maybe I'm not following.
Yeah, no, I think that's about right. I mean, you obviously want to turn Fourier transform into something more abstract, right? But I'm saying, can you like do the categorically abstract essence of Volterrification?
Yeah, doing the more abstract Fourier transform stuff is not hard, right? You just look at the spectrum of like the Laplace operator or whatever.
Yeah.
But okay, I have to ponder what you said. Yeah, that's an interesting point about the representables and whether or not there's an analogy there. Okay, we good?
Thank you.
Thank you so much for.
Okay, so right, Noah Crane is speaking the 25th, so that's next week. Yeah, next week. Anyways, thank you very much.
Yeah, thanks for the